Good evening, everybody. Welcome to tonight's edition of the Triangle Area SQL Server User Group's Data Science and Business Intelligence meeting. Tonight, I'm going to talk a little bit about machine learning operations. We're going to look at using GitHub Actions. We'll look at deploying Azure Machine Learning and learn a little bit about MLOps along the way. So if this is your first time to a TriPass stream, welcome. We're the Triangle Area SQL Server Users Group located in the Research Triangle area of North Carolina. So that's Raleigh, Durham, Chapel Hill. My name is Kevin Feasel. I am a data platform MVP out of Durham. I'm the president of the Triangle Area SQL Server Users Group. I'm the person who's usually hosting these things and the voice of the people when we have other presenters. Tonight, I am the presenter, so I will be all of the voices. However, my favorite Greek chorus. If you have any questions, drop them in chat along the way. I'll have it right down here, so I'll be able to see it as we go along. So let's get talking about machine learning operations. Quickly before that, by day, I'm a data scientist. By night, I do a little bit of consulting with an individual company that I run, small LLC, called Catalyxy Services. I also have a blog called Curated SQL. The idea of Curated SQL is every day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. So it's curatedsql.com. What we are going to do in this talk is, first, I'm going to make myself just a hair smaller so that I'm not covering up the motivations. But I'm going to talk a little bit about DevOps and data ops and its eventual flow into machine learning ops. We'll look at a code-first Azure ML model very briefly. Then I'll talk about the MLOps maturity model and look at how we can automate Azure Machine Learning pipelines using GitHub Actions. As a quick note, GitHub Actions is not the only way to do this. You can certainly use Azure DevOps pipelines or any other CI/CD tool of your choice. You're probably going to be able to work with Azure Machine Learning for deployment. I happen to like GitHub Actions a lot, so I'm focusing on that for today. Oh, I've messed myself up slide-wise. There we go. So as a brief idea of what we're going to do, we are going to look at some code. I've already created it. We're not going to create any new code tonight, but we'll look at it. We'll see how it works for building an Azure Machine Learning pipeline. We'll take a GitHub repository, and we've got our code in there. I'm going to create or use a series of YAML files that describe GitHub Actions workflows. We're going to deploy some of these actions, basically pushing out machine learning pipelines and eventually getting results in Azure Machine Learning. So we'll be able to see a pipeline running. It's going to take too long for us to see it through to fruition. As you can see, the timings, we're looking at roughly an hour for training to happen. So we're not going to have time for that tonight. But I can at least talk you through the process. And if you kind of look at the board, there we go. Directions are hard. If you look at the boards, you'll see I've run this several times. So there won't be any mystery behind it. Let's talk a little bit about operations of various sorts. The wherefores. So in our battle days, and I'm going to move myself up to the top so that we can see the whole thing. Basically, we have what I consider an incentive compatibility, an incentive alignment problem. We have developers, we have administrators. Developers, their job is to write code, is to push code out, is to get things out into production. Product managers are telling them, hey, we need you to write this code, we need you to push this thing out. Meanwhile, administrators, their job is keep the systems running, keep the servers going, make sure that nothing fails. Their tasks come from internal IT management. They're not working with the product managers. They're working within the realm of IT. Well, you can see the immediate alignment problems in here of we have developers who are pushing code. Administrators don't necessarily want code to go out because that code can break stuff. So they don't want to have the hassle of being on call, which administrators tend to be on call. Developers, almost never. And that's why we have long-running ideas and jokes about, oh, well, I'll just push this code out Friday afternoon at 4:30 p.m. and head out of the country. Incidentally, I did that once. People were not happy with me. I went to Germany for about 3 weeks, and when I was checking my email along the way, they're like, the code you deployed broke. Sorry, I can't access this from the plane or from the other country where I'm not allowed to remote in, so somebody else can fix my code for me. And administrators, they're the ones who typically get the pages. They wake up at 3 a.m. They try to figure out what in the world is going on with this deployment that has happened. And the developer is either asleep or drunk or in a foreign country, and therefore not going to be of much help. So we can see the problems. We can also see the problems that I have with simply using a clicker. Clickers are very challenging technology, I will have you know. But at the end of the day, this is incentive alignment. This is our core problem. And it's more difficult because the chains of command don't really meet until you get to the really high levels. What I mean by that is, if you think about developers, developers, they have developer managers, and they're also kind of working for product managers, not in a managerial relationship, but in these are the people whose job I'm helping with my code. Administrators, they report to different managers. They typically report up like 2 or 3 levels. Maybe you get to directors or VPs before these groups meet, and you have a common lead. Well, that means, we've got several layers of management in between them. And as a result, you're going to have different incentives. You'll have divergence. The idea of DevOps is we're going to try to minimize that divergence. This is a combination of people, practices, and tools, or people, practices, and processes, if you want the alliteration. The goal here is we want to solve some sort of incentive compatibility problems between development teams and operations teams. One important note, there is no such thing as a DevOps engineer. It is not a role. It is a set of people and processes. This is different groups of people, administrators, developers, who are communicating, working together to solve common problems in a way that works well, hopefully aligning incentives along the way. So it's not a new role, it's a way that people in existing roles work together. Also, as a note, the most important part of these are the people and the practices. The tools are the least important of the 3. And yet, as a bunch of introverts, tools are usually what we gravitate toward because people are hard and dealing with people. I don't want that. I didn't get into development or administration or data science or whatever when dealing with people. So like I said, we gravitate toward the tools. But the tools are the least important part of this. It is the people, it is the processes, the practices. It's those P's that matter the most, and not so much the T's. Couple of concepts of DevOps. Number 1, continuous integration, continuous deployment. The idea here is that we are very regularly checking in our code. When we check in the code, that's an opportunity for us to test our code, to ensure that things are working as we expect it to, that the code is building, it's compiling, it's running through tests successfully. That's continuous integration. Then we get to continuous deployment. And there's also continuous delivery that's sort of in between. But continuous deployment is this notion that I have code that goes through the process. It goes through the integration process. Tests are working. Everything's fine. Cool, ship it. Continuous delivery is an intermediary state where we've gone through integration, tests are fine, everything's good, and then a human looks at it and says, okay, I think we're ready to ship it. And they push a button. They George Jetson the code into production. So CI, we're checking in code and we're regularly testing that it is working as part of the build process, as part of an automated process that's running when we check in code. CD, the CD that I'm talking about, is we're automatically deploying this stuff out to different environments. And again, we could have additional tests. We could automatically deploy it to a QA environment, to a staging environment, run more tests on there, make sure that the code is working the way we want it to before it makes it to production. Another idea in DevOps that we see is developers building tools for operations. Those operations people are still the ones getting the phone call at 3 a.m., the pager alert. Well, we want the developers to build tooling so that operations people know what's going on, so that, oh, I have a spate of 500 errors that are happening in this application. Why is it happening? What's going on? What exactly is the error, and what's the cause of it? So we have developers who are more in tune with the needs of operations, building tooling, building functionality so that the operations person, who is groggy and probably also hungover, can check and see, oh, okay, this is the error that's happening, and have a better idea of how to fix it. But even if the operations people are the ones getting paged, well, developers are also involved. They manage their deployments. If the deployment fails, it's on development to fix it because the developers know the code the best. An operations person is not going to understand the code nearly as well as the developer who wrote the code, hopefully. And as a result, we're moving the onus on fixing the problem from an administrator to the developers. At a high end, you may even see developers who are on call, just like the administrators. So there may be a person who can't just leave the country on a moment's notice and try to get out of here. They've got to work with operations and get these changes out because at the end of the day, development and operations are collaborating. So it's not that we're taking a bunch of devs and a bunch of operations people and we're smacking them all together into one new role. It's more of these groups are collaborating and crossing boundaries that historically they haven't done so well. You see it on kind of a onesie-twosie basis where, oh, I know that sysadmin because I bought him a nice bottle of whiskey once, and now he helps me out when I'm in a problem. And moves into more of a institutional explanation of how these teams can cooperate. There's a lot to DevOps. There are some really good books on the topic. There are good trainings on the topic. In a lot of cases, this is a matter of practice that has to go through various levels of the organization. Now, we talked DevOps. Let me talk a little bit about DataOps, because DevOps is ultimately about shipping code and shipping code-related artifacts more effectively. By that, I mean tests, I mean documentation, I mean things that maybe assets that are used as part of the code. We want to push those out more effectively. But there's this big, important cylindrical thing that's in a bunch of architecture diagrams that DevOps doesn't really cover, and that is data. Databases are stateful. Applications typically are stateless. Applications are really easy to push out, to deploy automatically, to handle changes. Stateful databases, it's much tougher to change a database than it is to change an application. And so we have a new set of problems, and we have a new type of operations combination, DataOps. So DataOps says, well, hey, database code is code. It's not some special thing. Make that code part of source control. Make it part of your CI/CD processes. And what I mean by database code, I'm talking about table definitions, view definitions, stored procedures, even functions. I'm talking about even static data or reference data. We can still manage that in source control. And we need to be able to manage these changes over time. If I add a new column, then I need to be able to deploy that new column into an existing stateful database without destroying the existing state, without destroying the information that's in there. I need to be able to handle a variety of considerations like, well, what happens the second time I try to deploy that script to add a new column? It has to be idempotent. It has to be able to run repeatedly without fail and get me to the same end state. So we've got a couple of ideas that have come out of this, and then we could apply this to machine learning and say, all right, well, if DataOps is DevOps plus data management, MLOps, I would argue, is DataOps plus machine learning models. And these new models bring in a couple of challenges. So before I really get to the challenges, I do want to show off. This is an example of, I think this comes from Microsoft, and this is an architecture from the MLOps paper. So I'll drop that link to that in chat in case you're interested in seeing it. But let me talk through each of these steps. So in our first step, we train a model. Cool, so we've got our model, we've got some assets around it. Then we want to package that model up. We want to turn it into some pickle file or some combination of relevant model assets, weights, anything else that we need to run this thing. Well, we've got it packaged. We want to make sure that the model works the way we expect it to. We want to validate it. We want to run it against test sets. We want to run it against results that maybe we have some fixed inputs and we expect similar outputs. If it passes through validation, we want to deploy the model. We'd like to make it available for other people to use. And then after we deploy it out, we of course want to be able to monitor the model. We want to be able to know that it's working. If we get a bunch of error messages, we want to understand what the error messages are, why it's happening. If we see a significant performance improvement over time, we might want to understand, well, why did performance improve? Something must have changed. If we see a performance degradation, we definitely want to understand that, because we may decide, oh, performance is degrading because the underlying circumstances have changed from when we last trained the model, so perhaps it's time to retrain the model and we start the process over. So the reason that I dove in on this image is this is actually the same thing as the development process. We write our code, we build our code, we compile it, we test our code, we deploy our code out onto servers, and then we make sure that the code is working. And every once in a while, we have to come back and change the code because underlying circumstances have changed. Well, that flow here is basically just a regular application development flow if you think about it in those terms. And that allows me to envision machine learning development and deployment as another branch of application deployment and development. But it comes with a couple of difficulties, a couple of challenges, because one thing is we need to manage large data sets for training. Large can range from several dozen megabytes to several dozen terabytes, depending on what your company is doing and how expensive your training process is. A file that's a couple dozen megabytes, checking that into source control, not that big of a deal. Maybe a little bit of an annoyance, but usually not a big deal. If I try to check in a 2 terabyte file into GitHub, not going to happen. If I try to check it into a regular Git repo, not going to make a lot of people happy, because assuming they even have 2 terabytes of space available to download this, every time you change the file, you have a Git history, and that history involves changes to files. So if I already have an enormous file, any changes that I make to the file over time to incorporate new data, I am now blowing out the size necessary to even grab the Git repository and make it available on my machine. And that's assuming that Git doesn't explode on file sizes that large. Historically, Git tends not to work very well on really large files. Where I say really large is, let's call it 2 to 4 gigabytes. Above 4 gigabytes, you have problems in Windows. Below 4 gigabytes, you just have networking problems and making people really mad because the file will change, and now I'm taking up several more gigabytes of space to store the history of changes to that file. There is Git LFS for large file storage, and Git LFS works pretty well. There are other tools that are available for large file storage. One of my favorite is called DVC, Data Version Control, and that allows you to store those files in someplace like S3 or Azure Blob Storage or on a network. Nonetheless, we have to manage those files. We have to manage that data set for training because we've got to know what did we use to train the data, whether that's because regulators are going to ask us that or because we just want to understand what were the circumstances when we trained this model so that we can understand does it differ from today's circumstances. We want to be able to train models, deploy models, and retrain those models in the same CI/CD style that we use for application code and for database code. And also manage those trained models over time because I want to understand, is this model less accurate. Maybe I can train a new one and compare it. Well, I want to be able to compare apples to apples and understand that I'm not just chasing noise with my new models. That, this model is more efficient than the past model, except that when I train them both against, or when I test them both against data neither has seen, they're actually just essentially the same. I'm just chasing the noise of what's existing today and not actually getting a real improvement. You can see that if you have multiple iterations of that model over time and you're able to compare them using multiple different training data sets or test data sets. So we've got all those ideas. Now I'm going to talk a little bit about what I mean by a model. As a quick note, I'm only going to cover this at a very high level, and that is because I have an entire talk on building a code-first model in Azure Machine Learning. I also have a whole series of YouTube videos. It's about 25 to 30 videos spanning 3 separate talks on getting started with Azure ML, doing code-first Azure ML, and then this on machine learning operations with Azure ML and GitHub Actions. So I'll drop a link to that. It's also the same YouTube channel where we host all the Triangle Area SQL Server user group videos, so you can see those. But in the meantime, that link is for my talk on Azure Machine Learning, getting beyond the basics with Azure ML. I'm only going to talk about the code at a really high level, and let's get to a demo. And incidentally, if you just popped in, if you have any questions as we're going through this, please do feel free to ask. Drop it in chat. I can see chat at all times, which is slightly creepy if you think about it long enough. All right, this is a Visual Studio Code project. I've just got a folder that has quite a few files in it, and I also have a little cheat sheet here. So we're gonna review a data set. I'm gonna pop up Azure ML Studio, which means that I need to bring up Azure ML, and I need to switch directories. Let's go to my default directory. And I'm going to go to this CS Azure ML. I'm also going to zoom in just a little bit so that it's easier for you all to see. In my data assets, I've got several different data assets, and the one that I'm going to be pointing out right now is this Chicago parking tickets folder. This is a folder. It has files in it. It's in this workplace blob store. This is a Azure blob storage account that I created when I created this Azure Machine Learning workspace. Inside of there, I have some files. If I check out Explore, we can see that there's actually one file. It used to be called chicagoparkingtickets.txt, and it has information on, if I scroll this, these are parking tickets from the city of Chicago, Illinois, over something like an 18-year period. And so we've got quite a bit of information, including whether or not the payment is still outstanding on that ticket. Meaning, if somebody either has not paid the ticket and a judge hasn't thrown it out and they still owe money on the ticket, then this will be marked as a 1. If it's marked as a 0, it means they paid it or judge threw it out or whatever circumstances may be, this person no longer owes money on this ticket. So that's the general idea of the type of problem we're trying to solve, is whether we can understand what drives payment as outstanding. Can we explain it using other information that we have from this data set? So I've got a data set in here. I also have a note that this is publicly available and you can grab it from this link if you so desire. I'm going to look at deploytrain.py. This is a Python script that uses Azure Machine Learning's SDK v2, version 2 SDK. We have quite a few different calls here. I know that it's v2 because it uses azure.ai.ml. If you look and see something like azureml.core, that's v1. The v1 SDK is still available. It is still in use. There are some things that actually are still easier to do in v1 than v2, but v2 is where I tend to gravitate toward because that's the one that they are keeping up to date and that they are putting the most effort into. I won't dive into the code here because, again, there's an entire talk about that. What I will very briefly note is that we have a few different concepts. We've got a workspace, and that is my Azure Machine Learning location. It's my overall high-level controller of machine learning jobs. I have a cluster. That is one or more machines that I'll use for training or for scoring. I have a client that I'm creating, so I'm going to connect to that workspace using some credentials, and those credentials I get from the Azure CLI. And so I've got the Azure command line interface application installed on this desktop. I'm already connected to my subscription. Everything's all set up. We're going to load the workspace and then make sure that I have a compute cluster. So that way I have some machines that I can train on. If I don't, I will actually create a compute cluster so that I can use it. Then inside of this config directory, I have a series of YAML files. Those YAML files describe how I'm going to work with my code, each step along the way in a pipeline format. So I've got a component here that is feature replace missing values.yaml. So if I go to the YAML file, I will have some information that will say, oh, well, the input is called input data. It is a folder. So we're going to get a folder with information. Then our output is going to be called output data, and it will also be a folder. We're going to write out to a folder. Our code will be in a scripts folder, which is this folder right here. And specifically, we're going to run a Python script to execute feature replace missing values.py, sending in the input data, expecting to get out the output data. So the environment, we are going to execute this is all in Docker containers. So the Docker container that we care about is running LightGBM 3.3. It is the version 2 of this. Some of the packages have been updated. But this is a Docker container that Microsoft has built and made available to us for easy use. I didn't need to build a special container of my own. Inside the Python files, we've got some whatever preparatory work that we need to do. I'm argument parsing to make sure that the input data and output data parameters are available in the call. I'm writing out for diagnostic purposes some results, and then I'm reading through each file in the list of files of input data. So for each file in that folder, I'm going to perform some action. Specifically, I will create this in a data frame. I'm going to use pandas read CSV, grab the data, and put it into input df, and then I'm going to create a list, file list. So that's all of my data frames as a list. I can concatenate them together into one big data frame, and then do the actual work that I expect to do. So question in chat, where do the data assets come from? Ultimately, this came from Daniel Hoopmacher's work on turning an open data source that he got into a SQL database. I took the SQL database, I did a bit of work to extract out that payment is outstanding and to shape the data, and then I put the file into this blob storage location. I've also uploaded it into Azure Machine Learning. So I have a data asset in here, Chicago parking tickets folder, where I uploaded that file. So that's how Azure Machine Learning is going to be made aware of the existence of this data. Where I got it from, that's the prior steps. And if you want to try to replicate it on your own, I would start with this file right here, because that's where I've already performed the SQL work to clean it up a bit and get the columns that I expect to get. So hopefully that explains the question, the location. All right, so we go through this. There's a whole series of these elements, and the motif of Azure Machine Learning is that you have a pipeline. This is different from CI/CD pipelines. This is an Azure ML pipeline. This is a set of code that operates step by step. We have data that's passing through those steps, and we're reshaping it, we're refining it, maybe adding features, removing features, doing whatever it takes for us to get the data ultimately into a location to where we can train the model. Before that, I do have splitting the data into training and validation subsets. And then I'm training the model, and I'm going to register that model in the end. The way that I'll train the model is in this Python script. I'm kind of bouncing through here. In the other talk, go through in much more detail. But for this, what I really want to get is just a really high level of how this code works so that we can understand what machine learning operations, how we're going to set up the deployment process. So we're performing training. We have a function called process data. That process data is going to split out columns. It's going to reshape the data, set the appropriate data types, set some of these as categorical, set them as others as float. We'll have a train function that will reshape the categorical data and one-hot encode the results. And then I'm going to use gradient boosting as my classifier here, and I'll use that to classify. I could use like GBM, I could use XGBoost. I just used the gradient booster in scikit-learn just to keep things a little easy. We train the model. When we're done, we register the model. I've got a series of scores: F1 score, precision and recall, accuracy, area under the curve of the receiver operating curve, characteristics curve, and I'll write those values out so that I have those for future reference. That's part of registration. This is all happening in a pipeline. This is my Azure Machine Learning pipeline, and each one of these steps, this is how I tie together the individual steps. So each one of these steps takes in some input and gives us back some output. Well, the way that we make this a pipeline is our input data for the first step is raw data. That's what we get. That's what the function is getting passed in. Our next step, so it's called step replace missing values. Our next step is step feature engineering. As the input data, we are getting the output data of the prior step. And then we're going to replicate that for each step in the process. So that's how we get the pipeline. Each output step becomes the input to the next step. We have split data, which is splitting into training and test subsets. And we are going to take train model, and it will take a train data set. It will take a test data set and some hyperparameters of how we're going to invoke this gradient boosting classifier, Then we register the trained model and return out a model and a report. This function, prepare pipeline job, this is saying, all right, we have our pipeline. So that's this build pipeline function, and it has a pipeline decorator on it. And then we prepare a pipeline job. This is our preparatory function that we will call in our code down near the bottom. What we're doing is we're saying, I need to get the Chicago parking tickets data set. So this is where we are reading that data asset. That's where we get the folder, and I know that its input type is a URI folder. That becomes raw data. I call build pipeline, sending in that folder contents. Then I'll set a couple of parameters and return the pipeline job. We call the pipeline job preparation, and then we have a prepped job, and then I can create or update that prepped job and run this against the experiment named Chicago parking tickets code first. I could take this script and I can run it in a terminal. I could open up a terminal right here and call python deploy-train.py. It should work just fine. But that's okay for a data scientist working on his own laptop or his own desktop. It's not such a great solution for a larger team or for long-term operation where I want to have various iterations of a trained model. So we need to do a little bit better than that. I also do have a scoring function. The scoring function, I do have Azure AI.ml. I am performing some level of scoring in here. I'm basically saying perform batch scoring. I expect to have some input file or files, and I want to perform batch scoring on those files. I'll have a few pieces of detail around the deployments, around the environments that I do talk about in the other talk. It's not so pertinent for this talk because here this is mostly around taking the endpoint, making sure the endpoint is available, and then scoring against it. So we'll need to have this script if we want to score data. We'll need to have this script if we want to have an endpoint available to accept files and run those files against the trained model, basically to do something interesting. But we're not going to drill into the details on how this all works. That's what the other talk is for. So, all right, we've taken a quick look at the data. Now I want to get back and I'd like to talk a bit about machine learning operations before we actually get into the operations itself. The MLOps maturity model. There are a couple of different maturity models that I do like. Microsoft and Google, they have different maturity models. Microsoft's is a little more fine-grained, so I'm going to review that model, but the Google one is also good. There can be differences between the two. Nonetheless, I think that they're much more in common than they are different. And there's going to be a lot of text on here. I grabbed these specifically from Microsoft's white paper on MLOps. I'm just going to tell a story here. I'm going to tell a story at each level, so I won't read from the screen so much. But level 0, we have no machine learning operations. Our data scientists live in silos. They're not really communicating with anybody else, with the data engineers, with the software engineers. I would throw in database developers or database administrators because they're not necessarily the same thing as data engineers. Nobody's talking to each other. Data engineers don't communicate with other people. Software engineers don't communicate with the other groups. The data scientists are gathering some data. Like they're asking data engineers, hey, can you grab me this data set? And then that person will write a SQL query and save it as a CSV and put it in a share drive someplace. We're not managing compute. Everything's happening on the data scientists' laptops. We're not really tracking experiments. We're not checking to see how the training process works. And we kind of just end up with, here's a model. I've created a pickle file. How did I create it? I created it manually. If I have any sort of scoring, it's just some scoring script that I've created after the fact. And how do we deploy this thing out? Well, for application deployment, the developers, the software engineers have to sit down with the data scientist and say, well, how the heck do we use this thing? How do I make a call to this? It's a pickle file. I've never worked with this before. What are we doing? There are no, if there's documentation, it's limited. It's the data scientist saying, oh, no, you have to reshape the data this way because that's what I expected of you to do. And we're doing manual releases. We're having somebody take a folder and put it on a share drive or put it on a server or something along those lines when we have a new version of a model that goes out. There's a lot of pain. There's a lot of points where things can break apart. Then we get some DevOps fever. The software engineers, the data engineers, the data scientists, they're still siloed. But we're starting to see some automation. Like data pipelines are gathering some data automatically instead of having the data engineer go and write a SQL query, a one-off SQL query, and then save the data into a CSV and post it on a share drive. We might be managing compute. We probably aren't managing experiments, and we still have the end result is, well, here's a pickle file, and here's some H5 model weights or whatever. Our release process is still manual. We're still creating scoring scripts after the fact and still trying to do that handoff with devs. Where we see some growth is we're getting some integration tests. The application developers are writing tests. They're trying to understand the process a little bit better. We still rely on the data scientist to explain what's happening, but at least we're releasing automatically. We're getting into CI/CD for the application code. And the application code has got unit tests, integration tests. Things are hopefully working between model versions, or as a new model version comes out, it breaks a bunch of tests, and then the data scientists and software engineers have to work together to try to figure out, well, when do the tests need to change? When is the model actually functional, or has there been some problem that we've introduced? So you've got some level of growth. Level 2, we start getting into automated training. So data scientists are actually working with the data engineers, and the software engineers are still out in their own bubble. For model creation, we are gathering data automatically and managing compute. It's no longer happening just on a bunch of different laptops. Maybe we have centralized compute. Maybe we have virtual machines that the data scientists are executing code off of. We're tracking experiments. We could be using MLflow. We could be using Azure Machine Learning's model tracking processes, or the experiment runners. But however we're tracking these, we are keeping track of, this run of this trained code gave us these outputs, but then the prior run, we tweaked a hyperparameter and we had some different outputs. Let's compare the two and see how the models are. We're version controlling. So we're storing the training code and the models in source control, which is a big change. It's no longer just I've put the pickle file on a shared drive and now I'm going to try to copy that out to the app server. Model release is still manual. We haven't gotten everything, but we do have a scoring script. It's in source control. It's along with any tests that we have, and the software engineers are starting to manage the release process. Over on the right-hand side, application integration has stayed the same. Maybe we're adding more tests. Maybe we're getting more comfortable in how we're performing DevOps. And then we move up to this level 3, automating model deployment. Well, data engineers are working with the data scientists. Data engineers are working with the software engineers. Data scientists and software engineers still aren't closely cooperating, but we're getting to a model release phase where we're automating release, no longer copying files manually. We have those scoring scripts. We have a release that's part of a CI/CD pipeline, and I'll show you an example of how we can do that. And then you get to level 4, full MLOps with automated retraining. Everybody's cooperating together. Data scientists work with the data engineers. Data scientists work with the software engineers. Data engineers work with the software engineers. Everybody's working together. They're all trying to pull the same way to get the same end result. We have automated data. We have automated retraining that may trigger based on production metrics. Our accuracy over the past 30 days has decreased. We've hit a threshold. Now it's time to retrain and see if we can get accuracy back up higher. We're managing compute. We're tracking experiments, and everything's in version control. We're automating releases, and our scoring scripts are in version control. They're running automatically. Our application has unit and integration tests for model releases. Our data scientist doesn't have to sit there with the software engineers and explain, I added this new parameter in here, and as a result, it's breaking your existing code. We're coordinating with this beforehand. We're catching these issues early on and making it so that by the time something does go out into production, it's hopefully not going to break. So that's the idea. Those are the different levels. And I just want to point out that within the context of a team, let's say you have a data science team or a group of data scientists and data engineers and software engineers. We could have differing levels of MLOps maturity for different projects. I'll give you an example. Up until about a year ago, I ran a predictive analytics team. And on that team, we had a series of projects. Some of those projects I would describe as maturity level like 1, maybe 2. Some of them we were at 2 or 3. Some of them we'd gotten up to 4, especially the newer projects. Some of the newer stuff, we were really getting mature structure around how we developed things, how we delivered things, how we automated retraining. It takes a while for a team to get to that point. Now I'm a data scientist full time, and I would say that we're probably in the 0 to 1 range for most of the projects that I'm working on. That's going to go up. We're going to make that improve over time. But part of this is just understanding where you're at and what things you can do to move to the next step. And also understanding, when does it make sense to stop? There is a diminishing marginal return to automation. There are times when you say, this is good enough, and we're going to stop at that point. So I think it's totally fair to ask that question and to try to come up with, what is my right answer for when do we stop? How far does it make sense to go? If it's a one person, one data scientist at a company, then we may need to automate a little bit more than if you have 20 data scientists at a company. They may need to automate just a little bit less because you've got more people working on more projects and more capabilities. Just a couple thoughts that I'm throwing out there. And again, if anybody's coming in just recently, welcome in. If you have questions, drop them in chat. Happy to answer them whenever. But in the meantime, we're going to talk about connecting GitHub and Azure Machine Learning. These are both Microsoft products. You would think it's really easy to connect. It's moderately easy. So let's talk about our security architecture. It's a simple idea. What we've got is Azure Entra ID. Azure Entra ID used to be known as Azure Active Directory. In the documentation, half of the documentation, it's still known as Azure Active Directory, but it's neither here nor there. In Azure Entra ID, we have our users, we have security resources. Now we also have an Azure subscription. That Azure subscription contains, inside a resource group, Azure ML workspace, as well as Azure Blob Storage, log analytics, we have Key Vault, we have a couple of other assets that are going to be necessary, a container registry. So we've got all these things in our resource group. For the time being, for this talk, we're not going to need any of those other resources. We just need to focus on, I've got Azure ML, and I would like to store my code in a GitHub repository. So we've got our code in a repo, and then ultimately, I want to be able to execute this code in Azure ML. Our intermediary is a GitHub runner. A GitHub runner is just a virtual machine. It is either a GitHub hosted virtual machine, which is a VM in Azure, or it is a virtual machine or a physical machine that you are hosting. So if you have control of a VM, that could be your own Azure VM, or it could be an on-premises server. You have to install a GitHub runner agent, and then it becomes available. So we have our virtual machine. Our virtual machine is going to grab code from this GitHub repo, and it's going to try to execute that against Azure ML. Well, to do that, we need a couple of things. First, we need a recipe of how to execute that code, and that thing is called a GitHub Actions workflow. The other thing that we need is we are going to need permission for this virtual machine to access this code, this Azure ML workspace to run this code in the workspace. Just because you're a VM doesn't mean, hey, I get free access to your Azure ML workspace. We need to be able to lock that down. I don't want random people wasting my credits, wasting my money, executing and training their models in my Azure ML workspace. So I need to lock this down. And the way that I do that is I have a certain set of secrets. I have some information that allows GitHub and Microsoft and Azure to communicate and explain to each other that, yes, this particular runner is allowed to execute code on this particular Azure ML workspace because it is holding some bit of information. And there is a mention here that GitHub runners can also be containers. You're absolutely right. I am using VMs I suppose I'm using it in an overly broad sense, but they would be containerized on top of a virtual machine if you're using the GitHub hosted runner. So you can do it that way, or you could have a container that you've got in a registry that It's still going to run on a VM somewhere or a physical machine somewhere. But you're right about containability. So how are we going to do this? Well, let's walk through it. I do have images because there are a few steps in here that require things like a subscription ID, which I'm not going to show. We also have just the fact that this takes a couple of minutes and there are a few things I need to copy and paste. We need a resource group name. That's where our Azure Machine Learning workspace is hosted. In my case, it's called CS Azure ML. We need our subscription ID. Trust me, I know what it is. It's a GUID. We then say, okay, AZAD. So use Azure CLI, Active Directory, because, well, they haven't updated to Azure Entra ID yet. Create an application. And I'm going to call it Chicago Parking Tickets MLOps GitHub Video Demo because terseness is not in my vocabulary, apparently. When I say an application, the application registration that we're creating in Azure Entra ID is not so much this is an executable point and click, double click on this .exe and it runs. But it's more of a promise that we're going to do something interesting. We're going to want to have some hosted operation. So that's what we mean by app in this case, or an application registration. We create this, and it's going to spit back some outputs, including a couple of really important GUIDs. We've got app ID, we've got ID. I'm going to take those values. I'm going to copy them. I'm going to save them as app ID and object ID respectively. Then I will create a service principal. So our service principal is how we're going to be able to control the rights of the account, the application registration, that we're then going to give some token to the GitHub runner to say, yes, I want to execute this on behalf of the service principal. So I create my service principal based on that application registration. That's going to give me back some results. I have an app owner organization ID, which is otherwise known as a tenant ID. And then I have the ID of the service principal itself. I'm going to need both of those. I'm going to take those. I'm going to save those as tenant ID and assignee object ID. And then I'm going to create some role assignment. So this is where I take the service principal and I will say, you, service principal, you have permission as a contributor against this subscription ID, this resource group name. So my subscription and the CS Azure ML resource group. You are a contributor on any assets inside that resource group. That way, I'll be able to, if I can invoke the service principal's rights, I can then run code against that workspace. I can start up or stop virtual machines, the CPU cluster that I showed in the demo code earlier, or whatever other compute targets we have. Great. Next thing I need to do, in GitHub, in the Settings tab, over on the left-hand side, we have Code and Automation. Inside of that is Environment. I'm going to create a couple of environments. This is not mandatory, but if we're thinking in terms of CI/CD, well, we probably have different environments where we're deploying out our code. Maybe we have a dev environment, we have a test environment, we have a production environment. Those are probably going to be different Azure ML workspaces that are hosted in different resource groups, maybe even in different subscriptions. So I want to be able to do this per environment. After that, I'm going to create a federated credential. The federated credential is how GitHub and Azure will be able to communicate with each other, and they'll talk and say, okay, the secret that you're sending in, basically it's getting regenerated on a regular basis. GitHub can talk to Azure and say, here's the current version of the secret. Azure will say, okay, yeah, that matches what I've got, and therefore you are authorized on behalf of this service principal to do whatever work we need to do. That's the general idea of what we're trying to do with this federated credential. So we're going to create the credential, and we've got a parameter file, credential development.json. This is for my dev environment. What it's saying is, hey, I've got my name. My name, again, because I am trying to break this, apparently, by having the maximum number of characters allowable. I'm on the hunt for that always. But my issuer, token.actions.github-user-content.com. GitHub Actions will be able to run this. Other groups will not be able to run this. So this federated credential is specific to GitHub integrating with Azure. Like mentioned in here, no more static passwords. Yeah, and also, so no more client secrets. That's the other way that you can do it. You can generate a client secret and then take that client secret and save it as a GitHub Actions secret. But that means you have a static client secret. And if it escapes, if somebody accidentally pastes it and checks it into source control, or if it leaks somehow, well, now I have to change the secret. Now I may break some code downstream. I have to manage it. Kind of annoying. Here, we've got nothing to manage. All of this is just constantly updating. It's managed by GitHub and by Azure. And then I have a subject. The subject says the repository Feasel KL / practical MLOps, et cetera, and the environment development. So you are allowed to use that repo, that account name, or that either the enterprise account, the GitHub organization, or the individual user account, that repository specifically, that environment specifically. If you're not coming from there, GitHub's going to say, this credential is not going to work for you. I'm not allowing that. Azure doesn't even get to the point where they allow or disallow it. GitHub is saying, that's not really where you're coming from, Jake. So our audience is the Azure AD token exchange. So this is how we're going to communicate with Azure Entra ID. And again, they haven't updated all the names everywhere. So I've got one of these for development. You can also imagine I've got one of these for production. And it's going to look very similar, except that the environment will be production. So we create those federated credentials. Then I'm going to take my app ID, my tenant ID, and my subscription ID. These are things that I don't necessarily want leaking out, but none of them is technically access. None of them is access on its own. But I'm going to take these. I'm going to create GitHub Actions secrets. So in the settings menu on the left-hand side in security, we have the Actions tab under secrets and variables. And I will create one repository secret per environment, per secret type. So you can see 2 for client ID, 2 for subscription ID, 2 for tenant ID, 1 for prod, 1 for dev. Once I've got those in place, those GitHub Actions secrets are things that I can reference in my GitHub Actions workflow. As a quick note, there is no way that I can see the contents of this client ID from the GitHub UI. There is technically a way that you can find it. You can reverse engineer it through the GitHub runner. You could print it out technically. It's a little difficult to do, but it is possible. So there are ways that you can get the value of the secret, but nothing within the UI. So if a bad guy gets access to your GitHub system and has enough permissions to even see the GitHub Actions, that bad guy could potentially replace a secret and mess you up, but cannot read the secret. It also means that if you forget what your client ID is and you don't remember how to get to it, you may be stuck. So don't expect to be able to read that later. All right, we've done all the security prep. Now let's talk about GitHub Actions. Let's talk about the operations and deployment part. Quick overview of GitHub Actions. We have GitHub Actions workflows. A workflow is a YAML file that is going to execute and do a set of work. That is represented here as the entire box. Inside of a workflow, we have one or more jobs. The job is going to perform some purposeful set of activities. Each job is made up of one or more steps, and each step has an action. And that action can either be something that is maybe execute a script, or it could be call a GitHub action that exists outside in the outside world, like this one, action/checkout at v2. and we're going to do something. So this is where these are the things that tell us what we're going to do. Let's take a look at some actual GitHub Actions. So to do that, github.com, let's find me. That's me. Let's take a quick look at Practical MLOps with GitHub and Azure ML. That's also me. I have already, I'm going to zoom in a little bit further. I have already created my actions. So we have our client IDs and so on. Those are environment level secrets. So we're in good shape there. Link to the repo, absolutely. Let me drop one here in chat. I will also give a link to the whole set where you'll get the show notes, you'll get slides, demo notes, links to additional resources, links to a series of YouTube videos I've got on the topic. So that's the repo itself, but there's a lot more that I'll show. I'll give the link at the end. So we have in here GitHub/workflows. Inside of here, we have 4 separate YAML files. I'm going to look at train model dev first. Train model dev, let me bump it up one more level, maybe 2 more levels. 2 more levels, there we go. At the very top of the screen, I've got a quick note on permissions. These permissions are necessary for logging into Azure, specifically ID token write. This is a permission that you'll have to set. If you don't set it, you will get an error message, most likely. Even if you grant read and write at the repo level, you're still going to need ID token. So I just have this in at the top of the action. Every GitHub Actions workflow has a name. This one is called dev train model. Every GitHub Actions workflow has an on clause. That on clause says, under what conditions will this thing run? There are a few dozen different possible clauses. I am using 3 such clauses. Number 1, workflow dispatch. Workflow dispatch is manual. I push a button and it runs. Number 2, if I push into the dev branch, and specifically if I push into one of these files. So we have anything inside of pipeline/configs folder. We have anything inside the scripts folder. We also, if we change deploy train.py, if we change requirements.txt, if we change GitHub workflows train model dev.yaml, the file itself. So this is going to execute if we push into the dev branch and modify one of these files. Alternatively, it will execute whenever I push the button to say execute. The reason that I have these paths in here is if I hop back to this code, this folder, we can see I've got cheat sheets. This is how I'm able to tell, here are my demos. Here's what I'm supposed to be doing. I have my actual code pipeline, but I've also got this presentation. So here's my setup, different files. I've got credentials. I don't necessarily want to check in, or excuse me, I don't want to run the workflow if I modify my presentation. That doesn't make much sense. So I'm going to specify just this. Then we have jobs. 1 or more jobs required for a workflow. The job here is deploy ML training pipeline, and the job has a name, dev deploy the training pipeline to Azure ML. That'll show up in the menu. It'll run on the latest version of Ubuntu that they've got available, which is 2204 LTS. It's going to run against my development environment. Incidentally, the environment names are just tags. Development doesn't mean anything as far as GitHub's concerned. It may mean something as far as we're concerned, but as far as GitHub's concerned, it's just a name. So I could call it development, I could call it dev, I could call it D1, I could call it not prod. I could call it production and have it be development. It'd be confusing, but I could technically do it. Inside of my jobs, we have steps. These steps are the individual actions that we're going to take. So our first action is repo checkout. We're going to use action/checkout at v3. The really neat thing about GitHub Actions is if I go to github.com/action/checkout. This is the GitHub action that I just referenced. And we have their latest version is V4. So I'm using V3 instead of V4. Still works. And then we have some examples of how you can use it. If you want to look into what is the code that is actually running in here, we can dig into it. So if you have a security team that needs to know what's the contents of this GitHub action that you're referencing, this is how you can look into it. So the actions are just in GitHub repos. The next thing we're going to do is install the Azure CLI. The Azure CLI automatically comes on these runners on Ubuntu, on Windows, or on Mac OS. But what doesn't come automatically is the Azure ML extension, the SDK v2 extension. So I'm going to make sure that we install it. Then I'll log into Azure, and I'm not sending in a client secret. I'm sending in my client ID, my tenant ID, and my subscription ID. And then GitHub and Azure will communicate, and GitHub will be able to send over the token, the generated token that it has. Azure will be able to, Entra ID will be able to compare the token and say, okay, yeah, no, this you do have legitimate access to this. So no passwords here. I could give you all three of these pieces of information. You wouldn't be able to do that much. I'd still rather not give them to you, but it's not as bad as giving you a client secret, because if I give you a client secret, then you can do whatever you'd like. One quick note, if I'm using this approach with federated credentials, I do need to enable a ZPS session. That is going to be required, otherwise you'll get an error. Next thing, I'm going to make sure that I have Python installed. As I recall, the GitHub runner actually does have Python, but I'm going to specify version 3.10 because it's a recent version that I have that I know works. I should probably bump this up to 3.11, but I'll do that eventually. Finally, run the YAML pipeline, and this is a run operation. So we're not using a GitHub action. The rest of these we were using GitHub Actions. Other people wrote that code. Here and install AZCLI, these are my own code that I wrote. So I'm going to cd into the pipeline folder and then install dependencies, running pip to install my requirements based on requirements.txt. We'll create a configuration file by making a directory called .azureml. .azureml is a special file, is a special folder, and inside of that folder, I'm going to create a special file called config.json. That config.json will have my subscription ID, will have my resource group, will have my workspace name. That combination of those three things, this is what we would need for our credentials. So this is saying get Azure CLI credential. But there is another way, a way that if you have this .azureml folder already in place, then it's not even going to look at the CLI credentials. It's just going to grab the credentials from here. We'll say, oh, yeah, I'll check that subscription ID, CS AzureML, and that workspace. And then I'll authenticate you there that way. And then we'll run our pipeline. So what is our pipeline? Python deploy train.py. That same script that I could have run on premises locally from my desktop, I can run it from here. A lot of this is just prep work to get us to the point where we can run deploy train.py. And let me just give it a run right now. So I've got dev, I've got train model. It has a workflow, a dispatch event trigger. I'm going to run it from the dev branch. Let's run the workflow just to see what happens. And there we go. It is currently spinning up resources. So let's take a look. I've got dev deploy the training pipeline to Azure ML. That was the name of my job. Inside of this job, I have a series of steps. So we're trying to log into Azure, check out the repo, et cetera, et cetera. We walked through all of these steps, but this is my UI that allows me to see what those details look like. Now, this is going to take a little bit of time. And while it's going, I'm going to show you another one of these pipelines, these workflows. And that'll give us some time to let it do its thing. If I go in and I look at scoring, let's look at scoring in production. The structure of this file, starts with permissions, just like before, has a name, prod score model, and we're going to run it on branches, just the master branch. So dev branch for my dev operations, master branch for my prod operations. This is a scoring file. The only time I want this scoring operation to run, this workflow to run, is if I change the data in the pipeline data folder, if I change the deploy score Python script, or if I change this GitHub Actions workflow. If I look at the data folder, let's take a quick peek at that. So I have pipeline, data. Inside of here, I've got a couple of files, Chicago parking tickets 1 and 2. 1 and 2 here are just a copy of some data in the shape that I need them to be without the value for payment is outstanding. Because what we're going to do is we're going to try to generate the results for payment is outstanding. And we're going to see what it looks like. So we've got our paths, and then we've got the job, deploy the ML scoring pipeline. It has a name, it runs on Ubuntu as well. The environment is production. So instead of it being the dev environment, it's a prod environment. We check out the repo. We install Azure AZ CLI. We log into Azure. This is all the same so far. We install Python. This is the same. Run the YAML pipeline. Literally, the only thing that's different in here is just this last line, deploy score.py instead of deploy train.py. And what I can do, let's look at this prod score model. It's been a while since I've run this, so let's see if I can give this a run and if it'll work or if it'll fail. Now I'm really living on the edge because you can see this is not something that I consistently run. Oh, good. Stuff is happening. We're installing the AZ CLI. So we've still got a couple more steps to go. But what I'd like to do is say, well, what's happening? What are we actually seeing in here? And what we're seeing is we're executing a GitHub Actions workflow. That GitHub Actions workflow will eventually kick off an Azure Machine Learning pipeline. So what I expect to see is in Azure Machine Learning, we're going to go to jobs and we have an experiment. I have an experiment here called Chicago parking tickets code first. In our code, we're writing to that experiment. If I return back to the code for just a moment, I'll go to the deploy train script and here's my experiment name, Chicago parking tickets code first. So that's how we're controlling where we're writing it out to. It's just in our training script. Inside of this experiment, I have a whole series of different runs that have happened over time. The last time it ran was March 9th of 2024, but we can see if I select this training pipeline, we have different steps. Replace missing values, feature engineering, feature selection, split data, train model, register model. These are the steps in our pipeline that we walked through in the code. This is just a visual representation of that code itself. And our output data and our input data, they're folders that just feed into each other. And we can see how all of this works. I could drill in, I can learn more about this particular training operation. I can see how it performed. I may even compare it to others, to other operations. We can see that it took about 58 minutes for this one to run and that a service principal created it. I created this one. So this was me kicking it off from a GitHub Actions job. This was me kicking it off myself. Maybe I ran the code directly from a console. I probably did because that seems like that was right about the time that I did the presentation for TriPass on getting beyond the basics with Azure ML. So, all right, while this is going, let's go back and see if we can see what's happening. We are now post Azure login. Oh, we've got a green check. Green check is usually a good thing. It took about 4.5 minutes. Now, I already told you, it takes like 50 something minutes for this to run. So what gives? And what gives is I'm not going to pay GitHub to have a machine sitting there and spinning for an hour waiting for Azure ML to finish up its job. So I'm kicking that pipeline off asynchronously. And at the bottom, at the, I think it's somewhere around post Azure. Maybe it's in run YAML pipeline. Yeah, here we go. Now look in the Azure ML Jobs UI to see the status of the pipeline job. This will be in this experiment. This was just a print statement that I put into the training script. And that way it would remind me to go look in here. And we have a running job. So I didn't kick this off. The service principal did. If we go in, we can see that it's currently setting up resources. It's waking up some servers. It's deploying some containers, container images out onto VMs to let me run my operations. And that's what's going to take about an hour to finish up. Once it's done, then I'll have a newly trained version of the model. If I go over to the models tab, I've got a lot of different versions of this code first model because I've run these experiments many times before. Meanwhile, I want to look at my scoring. So let's check out endpoints. I have an endpoint. If I go look at batch endpoints, I have my Chicago parking tickets batch. I created this thing a while ago, and we can see that it's out there. It's using the first variant of the Chicago parking tickets code first model, because the secret is all the variants are the same. It's the same code. It's the same test data, same training data. We are not functionally changing anything, but it is running in Azure ML scikit-learn, running on, actually it's Ubuntu 22.04. It's just that this is this is the name of the environment, but it's running newer version of Python, newer version of Ubuntu, because it's version 33 of this particular container. And so I've got a job running right now, a batch scoring job that's executing. Well, if I go back over to my score model, that's what kicked it off. So I have this prod score model, and if I go in, we've got all of our steps that ran and ultimately kicked off Lime Truck that is waking up. It's got to use some compute, and then it's going to perform the scoring operation. So it may take another 10 minutes or so. It might actually take a little bit longer. Let's refresh. Might actually take a little bit longer than that, simply because I'm also using the same compute for training at the same time. And as a result, we may have jobs that one job gets scheduled before the other job, and this one came in later, so it may have to wait a little bit. It depends on how many of my 4 available CPU or my 4 available compute target instances I will get to run. Here's my cluster, CPU cluster. It's currently resizing from 0 to 1 node. If we keep it at 1 node, I may have to have a job queued up, or it may decide, let's get a second node. Let's have these 2 jobs run in parallel. Something that I don't necessarily have a lot of control over, but one of the nice things here, though, is that when I'm not working, I have no cost for compute. Basically, I have no nodes. I take that penalty of the startup cost and say, I would rather pay that 10-minute, 15-minute penalty instead of paying actual money when I'm not actively using the compute. All right. What we've walked through here, using GitHub Actions workflows, kicking off pipelines that then run Azure Machine Learning jobs. The Azure Machine Learning pipeline is where we're really going to train our model, perform testing, perform inference or scoring. That's where we're doing all of the work that we actually want. The GitHub Actions runners are there for us to get the code, deploy the code out, execute the code. And the workflows are our mechanism for telling the runners how to do the job. And that's the big idea for the tooling around MLOps. Now, quick idea of updates. I'm just going to talk through this. I won't actually perform an update, but very briefly, branching strategies. I've got about 10 minutes before I'm going to wrap things up here. So let's talk branching strategies, because, what other way to annoy people than to say, this is how I like to do branching, and then everybody's like, I like to do it differently. Go away. We have a single branch. I commit to that branch. This works well if you just have a single person who's working and you simply want source control. You don't need multiple branches. You can just have the one branch. But this stops working pretty soon when you have multiple people, because now people can overwrite each other's work. You can end up having some level of problem. So we get into this notion of feature branching. And the idea is that I'm going to start working on a feature. I'm going to reticulate splines. Excuse me, I meant to push the draw button, not the zoom button. I'm going to reticulate splines. Meanwhile, my coworker will be manifesting reality. So we're working on these, and you'll notice I started first. I branched off of the master branch and began working in my own branch. I'm committing within my own branch. Meanwhile, my coworker has has broken off from the master branch and created this new manifest reality branch and is committing. Those commits are not going to touch. I can have broken code in my branch. It's not going to affect the other person. I may check in code, oh, that's not working quite right, but it's the weekend. I'll come back to it on Monday. I just want to make sure that it's in source control. And then I can come back to it. I can have however many commits it takes to get the job done. Then I'm done. I'm happy with it. It's time for me to merge my code into the master branch. Cool. How does that affect the other developer? Not at all. Other developer can keep working. Now, at some point, the developer is going to want to pull the latest changes, merge the latest changes from master into that developer's branch. That way, if there is a conflict, we fix it in this manifest reality branch versus having the conflict go into master. We keep master as clean as possible. We keep it functional throughout this entire process. Eventually, the other developer finishes all the work, commits into master. So we have these feature branches that are breaking off of our primary branch, and then we are eventually merging them back in. This is an okay strategy. Not a bad strategy. Can be better with this idea of environments, because, well, now we have not just our production environment, which we can represent with, in this case, the master branch, but also we can have a development environment that is using a different branch. And so we broke off at some point the dev branch from master, and now we have operations. Well, okay, let's say that I'm working on a feature, reticulate splines. I am going to branch off of master, not dev. By the way, manifest reality is up here somewhere as well, and also is a branch off of master. I just didn't want to confuse the graph too much. So I'm doing my commits. When I'm done, I'm going to merge with dev. So I'm not going to merge it straight to master. I'm going to merge it into dev, merge those changes in. This will kick off some GitHub action workflow. Build code, test code, deploy code, maybe train model, deploy the model into a dev environment. Everything looks good. We're all very happy. Everything's working perfectly. Cool. I can merge it into master. And as a quick note, you may be saying, hey, wait, your code is in dev. Why not merge dev into master? And the reason is that dev may have some detritus that has built up over time. There may be some feature branches that made their way into dev that we never intend to move to master. Maybe the PM said, we're not going to do this. Or we decided we found a different way to do it. So dev has some mess that builds up over time. So every once in a while, we're going to essentially overwrite what's in dev with what's in master. We're going to bring dev back into spec with master. That will lose any of these unmerged feature branches that have gone to dev but haven't gone to master. And so this is something we would want to coordinate with the developers, make sure that, hey, on Sunday, next Sunday, we're going to do this. If you have code that is in dev that has not been promoted anywhere else, make sure you track it in your feature branch, because you may need to re-merge to dev afterwards. So we can do that. There is also this notion of release branching. where if we're deploying a specific version of a product, we may want to have different releases as branches. So I have my release version 5 or release version 6.4 or whatever. I think this is usually a bit of overkill for most projects. If you are building a product that then gets installed on machines, makes perfect sense. If you're running like a software as a service solution or you're deploying out models for internal company use, probably overkill. I would probably stick with something like environmental branching. So that's my very short version of strategy. Typically, I like to use environmental branching once I have multiple people involved on a team. And my reasoning is now below me. Dev and prod releases let you have multiple workspaces, and you can have other branches. You could have dev, you could have staging, you could have test, you could have prod, whatever. Azure ML will also track model history, so I don't need explicit releases in GitHub. I have the model versions in the Azure Machine Learning workspace. So if I come back here, by the way, I see, okay, succeeded 2 nodes. So I have 2 nodes running. It did decide, in fact, to give me a second node. And if I come over to models, this is my quick reminder. I've got like version 14 of the model, version 13, version 12. So I'm keeping track of these changes over time, and I can compare these versions of models if there were legitimate differences between them. I am just kind of curious about how Lime Truck is doing. It's currently running, so it may take a few more minutes to finish up, but it does look like it is actively batch scoring. So yeah, that's a good sign. It's a good sign. I'm not going to do a demo. Basically, what this would do is I would show off how to create the branch. I would show how we might check code in, and then how it kicks off each of those jobs independently, the different GitHub Actions workflows. Hopefully, seeing this, having us walk through it is good enough for today. If you do want to see it in a little bit more action, I'll link to the videos where you can get a little more info on them. So wrapping things up. Over the course of the last roughly 90 minutes, we've gotten some understanding of what machine learning operations is. We've learned about the MLOps maturity model. We've learned how to use GitHub Actions to automate Azure ML pipelines. If you would like to learn more, if you want to grab this slide deck, if you want to grab the demo code, if you want to get links to additional resources, that is all at csmore.info/on/MLOps. If you have questions, you're welcome to drop them in chat here, or please do feel free to email me or hit me up on X or wherever you would like. And if you go to this link, it will take you to my webpage. So you can grab the slides, you can grab the demo code. I have a lot of helpful links here, but also I have a playlist for Azure Machine Learning YouTube videos. So I can drop that in here as well. And oh, that looks like a very big version of me. So I've got this whole playlist that is 16 videos long and covers a lot of topics in the Azure ML space. You're welcome to check that out as well. With that, are there any questions? If so, get them in chat. Otherwise, we're going to round things out for the evening. And I'll take a moment and see if there are any questions. I'm hoping that this will actually finish. Hey, look, it finished. It succeeded. So we got our results. Everything is good in the world. And it looks like no questions. So I do want to say thank you all so much for stopping in tonight. I will post this video on the same YouTube channel that this playlist is associated with. That way, if you want to rewatch this video later on, you're welcome to do so. The Triangle Area SQL Server Users Group, we meet 3 times a month. On the second Tuesday, we've got our advanced DBA meeting. Third Tuesday is in person only in Raleigh, North Carolina. It is our main meeting. And then fourth Tuesday of each month is data science and business intelligence. We also have a couple of meetings every month on just called Shop Talk, where the TriPass board just gets together and chats for a bit. You can find all of these at meetup.com/TriPass. And with that, I want to say thank you all so much. And thank you, Rick. Appreciate you stopping in here. I saw your comment. I appreciate your comment as well. on that video that was there. But with that, I'm going to wrap things up for tonight. Until we see each other in a future meeting, everyone take care.